Okay, you are in the right place. We are here today to talk about batch normalization in cytometry. And if you're interested in playing around with any demo data sets, you can check them out at app.teiko.bio. So we're going to talk today about batch normalization in cytometry for dummies like me. And you're going to hear about how batch effects can hurt reproducibility and how normalization might help. I'm Ramji Srinivasan, co-founder and CEO of Teiko, and our mission is to make high-parameter cytometry on clinical trials simple, easy, and routine. So, who might care about this subject? It's basically any drug developer running 100 specimen plus clinical trials and using cytometry. And a lot of times those specimens don't show up at the exact same time. So these drug developers will run into this issue called batching. So case in point, across time, you could be receiving batches of, say, 30 specimens, batch 1, batch 2, batch 3, batch 4. These aren't run at the exact same time nor by the exact same person, and these could lead to what's called batch effects. That is, operator handling, instrument handling, variability, etc., means that these batches can't be compared directly. So we mentioned this phrase batch effect. What's that really mean? Simplest example is even outside immunology. If you think about weighing yourself, if you weigh yourself at the hotel or at the doctor's office, or at home, those could be 3 different measurements. And the variation may not matter that much for your individual weight, but when it comes to your cytometry measurements, it probably matters a great deal, particularly when you talk about pharmacodynamic assessment and reading subtle signals. So for batch 1 and batch 2, you could have these potentially false signals, which are dangerous since they could lead you to falsely believe you're seeing a signal, or conversely, you can miss a real signal. And both of those are very challenging and potentially dangerous for a drug program. So let's take an example. This is a single sample run in 4 different plates. P01, you're going to see the notation, and we're going to look at CD11B expression. You're going to see this real-life batch effect. So here's a single sample with CD11B expression on the x-axis. This is called a ridgeline plot. Basically, it's like a histogram, and this sums to 1 across all these expression levels. This is an uncorrected value. Now, we are going to run the same exact sample in another batch, and this is P02, and it's not exactly lined up. And then P03, and you can see this green line isn't lined up as it was in the first 2 cases, and then P04. So this same sample shows different expression patterns. It's the exact same sample. So this is what's called a batch effect, when the very same sample is showing these results that are all over the place. What is the goal of batch normalization? It's to get rid of false positives, false signal in your data set, and reveal true signals. On the left-hand side here, you have the status quo before normalization. In the x-axis, you have a bunch of different cell types over here. The y-axis, you have the p-values, and the number over here is 0.05. You can see here a bunch of things look like significant results, and these guys do not look significant. Then, applying techniques like batch normalization, you might be able to find out that some actual cell types you thought were significant are now removed owing to the technique, and others are revealed as truly significant. So this is really exciting to see this potential to find true signals in your data set that might be missed otherwise. Let's make this more detailed. So let's take an example dummy data set from a drug developer, and we're going to show how you can enable cross-cohort comparisons. So let's take the status quo. This is a $300,000 data set. Imagine a drug developer spent $2,500 per specimen, and at 120 specimens. In the first cohort, there are 30 specimens, which only allows you 435, which is 30 choose 2 possible pairwise comparisons. The second cohort, again, another 435 comparisons. The third cohort, same thing. And the fourth cohort, another 435, yielding 1740 possible pairwise comparisons. Immediately, you can tell that you aren't able to compare between batches 2 and 4 or batches 3 or 2. You can, but you'll risk this false positive issue we mentioned about earlier. This is where batch normalization comes in really handy. For the same dollar amount, you can run batch 1, batch 2, batch 3, batch 4, apply batch normalization, remove this technical variation, and then ultimately compare samples across all these cohorts, yielding over 7,000 possible combinations, which is a 4x increase. Obviously, this math gets bigger and better the more samples you send and apply batch normalization to. So how does it work? We're not going to do a full tutorial today, but depending on the algorithm, you usually normalize the data within a batch, cluster the cells together, group them together using similar marker expression, and then apply techniques to assign and renormalize the data. and remove these batch effects. So in cytometry, there are two popular algorithms, CyCombine and CytoNorm. These are some of the representative steps in CyCombine. You normalize, you standardize each batch's data using what's called a z-score, or potentially ranking. Then cluster, you use a technique called self-organizing maps to cluster cells into groups, capturing biological diversity. And then you correct, you apply combat, which is a great technique from 2007. This helps you, within each SOM cluster, remove these batch effects and maintain your biological signals. So let's apply this to our data set. So before, you remember this uncorrected expression of CD11B. These were 4 of the exact same sample, and they looked all over the place. Using batch normalization, these all end up in the same place. So this is great because our same sample should look the same, not depending on the batch that it's run in. So if you want more detail, check out our YouTube channel. We're going to be posting more videos on this subject and many like it. So subscribe to our channel and feel free in the comments to let us know what topics you think we should cover next. Thanks for coming into our channel today.